I had tried for a long time to take these nanomachines and have them drill into cells, drill right through the lipid bilayer of a cell to kill a cell. This would be a great way to kill cancer, right? The idea is that you put one of these molecules on a lipid bilayer, and then you turn these on, and they would spin, and they would drill through and pop holes in the lipid bilayer. If you pop enough holes in a lipid bilayer, that cell is going to die. So last time we finished up talking about nano dragsters. And we talked about how those will move toward a step edge. So if you heat it up, they'll move toward the step edge and then start going toward that charge at the step edge. Yeah, they move toward the step edge because remember, there's a charge buildup when you have this edge here, because there's these gold atoms all along the edges that accumulate charge because they have nothing else to donate into, because they're just kind of hanging off the edge. And so all of these spots are the dragsters moving toward the step edge. So you see that little by little, these are moving toward the step edge. And so they go toward that charged edge. So we also wanted to make nano trucks. Could we carry cargo? So that's the idea. Could we somehow carry it? And like there's a heme. So there's these 4 nitrogen atoms, and iron sits in the middle in your red blood cells, and that's what's carrying the oxygen and the CO2 back out. So could we make a nano truck like this? That was at least the thought. All right, and so yeah, it was, and so we ended up making this nano truck like this. We made nanoworms, and that capitalizes on an interesting phenomenon that if you have these diazobenzenes, so these diazobenzenes like this, then what happens is if you shine light on it, you go from the trans to the cis. So if, for those of you who took organic, you remember you could take a trans double bond, you shine light on it, it goes to the cis. That's the same thing happens with azobenzenes. But unlike when you have a carbon-carbon double bond, when you have that nitrogen-nitrogen double bond with 2 arenes on a side, if you heat it up, it will slide back. All right, that doesn't happen with alkenes. So there's a non-symmetric motion there. There's this, and then there's the sliding. So there's the shine light and then the sliding when you heat it up. And so because of that, the idea was to move it and then just keep pushing it along that way. Now, if it were just a symmetric motion, then you wouldn't expect it to move very well. But since it's a non-symmetric motion, the idea is to do that. And so you go ahead and we went ahead and built this. So you take this compound and you put on the alkynes, clip off the TMS groups with potassium carbonate and methanol, and do a Sonogashira coupling, and that will put these axles on. And so you can see that if you shine light on it, you get the cis, and then you warm it up, it goes to the trans. Cis, trans, cis, trans. And so this kind of works like that. We had wanted to make a Nanobackhoe, which we could make. We never demonstrated the operation. To demonstrate, the synthesis actually is much easier than actually imaging these things. The imaging takes a long time. Organic synthesis is a lot more advanced. It's been a field that for 175 years, organic synthesis has been going on, whereas imaging is a relatively new technique, maybe 35 years or something like that. So the analysis, the imaging analysis, takes much longer than the synthesis now.
If you do not believe in the physical resurrection of Jesus Christ, send me an email, tour@drjamestour.org, and we will get together, and I will share with you about why I embrace the resurrection of Jesus.
And so the idea was to have a backhoe where you could shine a light on this, get this to go to the cis, and then in that cis form, these 2 nitrogen atoms can chelate a metal, so they can chelate a metal, and then you could move it back, you could move it to where you wanted it, and then shine a different wavelength of light. It'll go back to the trans and drop off the metal. So you see that pick up metal and drop it off. So now you can do buildings, if you get enough of these building for you. So the whole idea was to think about bottom-up construction this way. We made all sorts of different wheels. And so you see the synthesis that you go through. And students love this stuff who like organic synthesis. They like to build molecules. It's just what they like to do. So they come in and they do this kind of coupling chemistry here. They do this coupling. They get the 4 alkynes, which would be the 4 axles. And then they put on this organometallic complex. So now you get this big organometallic complex. So these are really big wheels here that are on the edges of this. This is the space filling model. This is if you filled up the van der Waals radii. And so you can see the ruthenium atom is actually buried inside of this. It's very hard to see because you have all of these phenyl groups and these ethylene groups here. But anyway, so it has the big wheels on it. Then we wanted to try making self-assembling metal complex nanocars. So could you have 2 halves of a car, and then you drop in a metal between them, and they just start assembling? So you build you build half a car, and it assembles into a whole car. So here's the half cars in a solution without the metal added. And when you add the metal, the whole color changes, and you get these whole cars here. So that would be the idea. So we went ahead and built these structures doing the organic synthesis. So there's the half car, and here's 3 nitrogen atoms. And then if you put 2 of these together with iron would sit right in the middle and pull these 2 halves together, and then you get the whole car. So you see that would be sort of the arrangement here. And so that worked. So, when you see a yield here, I mean, that was the yield of the actual reaction. And so you can see here's the half car. As soon as you complex it, you get the whole car. And the color changes of the solution too. The half car, it doesn't absorb light in the visible region. If you just take ferric chloride, which is just yellow solution, you add the ferric chloride to the half car, and then boom, you got the complexed car. And then you're seeing the wavelength much further out. And the NMR substantiates this. Then there's a hydrogen bonding car. Just like DNA hydrogen bonds, you get the GC, for example, and they're hydrogen bonding between each other. Could you do the same type of thing, just take a half car and have it assemble into a whole car? You say, well, why are we doing this? They're like, why not? I mean, what do you want to do for a PhD? I mean, you're building new structures, new nanostructures. If we can learn to make cars rapidly, we could think about doing construction with them. So could these then generate full cars this way? So we just took this hydroxypyridine and that we iodinated, and we put the alkyne on it, clip off the TMS group, and then do the Sonogashira coupling. So now here's a half a car, but it doesn't stay as the half car. This dimerizes directly to the whole car. And we know it's dimerized because you can see in the mass spectrum, you can see the molecular weight that's consistent with the dimer, not the molecular weight that's consistent with the monomer. So this thing is dimerized directly to the full car. How about trains? Could we build trains this way? That's the idea. And so the idea is that if you can have some terminal wagons, so this might be like a caboose, and if you could make a covalent dimer, so that if you take these bromides and you're on a copper surface, copper will cause these to undergo what's called an Ullmann coupling, and that would make this covalent dimer. That was the idea. And or if you wanted just this to extend, you put the bromide on both ends and you have it extend. The interesting thing about this is that if we rotate, if you rotate about this single bond, that's going to place this ring up here, and this ring is going to end up down in this direction. So you see, instead of them being parallel, they'll be a cross correlation or anti-parallel to one another. And you can end up seeing that on the surface. So remember, there's this parallel conformation, and then there's this cross conformation. So when this is on a surface, we should end up seeing both. And that's exactly what happens. You put this on a surface and you end up seeing both. So you can see here's a parallel conformation. and here's a crossed conformation. All right, and you can tell by the distances here that this is right at the distance that this should be across. But what happened is that what we expected these to dimerize like this, that the copper would take out the two bromides and it would dimerize. But what's happening is the copper gets in between, it spits out the bromides, but the copper atom is staying in between. You say, well, why does that occur? And the reason that occurs is when you're in solution and you're trying to put two aryls together, two bromobenzenes together, what happens is they'll get on a copper atom and they'll be in a cis conformation. And from that cis conformation, the copper atom is ejected and the two arenes end up sticking together. But this can't get into a cis conformation. They're going to stay trans to one another. And the reason they stay trans is purely because they don't have enough freedom on the surface. It's not like they're in solution. So the copper can't move them to get the cis conformation to eject. So what we ended up, because you can tell by the length, so if the copper had been spit out from axial to axial should be 18 angstroms. But what it's turning out to be is to be 20.8 angstroms. And that means the copper atom is sitting in there. If the two bromides had remained in there, it'd be 25 angstroms across. If one bromide had been in there, it'd be 22 angstroms across. But it turns out this distance is right at 20.8 angstroms, this distance. And you can actually see between these, you can see copper atoms sitting between these. So you just take this half car, you just take this structure, put it on the surface, and what happens on the surface, it immediately polymerizes. So you can see this polymerization of chains. And once in a while, and so it's mostly parallel conformation, that should be the lowest energy conformation, but once in a while you see this crossed conformation, where the two axles are anti-parallel. So you can see this cross conformation here. And when you look closely, you can see there is the copper atom sitting on the surface, and this is the imaging was done by a colleague of mine, Leonard Grill, and his group, and the synthesis was done by Takashi Sasaki in my group. And so you get these polymeric structures, and this is what we expected. We expected these trains to form, and they form like this. So think about this. You can't build from the top down this small. You could never make large structures and whittle them down to a small structure like this. These are all made from the bottom up through organic synthesis, and then you just put these on the surface and they're pulling copper atoms off the surface to do this chemistry. Just a quick reminder, this organization is run totally by volunteers, but we do have to pay for the production work. If you could help us out by going to give.jesusandscience.org, we'd appreciate it, or you can click in the description box below. If you can't give, we certainly understand, but please just give us a thumbs up and click subscribe. Thank you. Now, if you come with the STM tip and you actually physically push this thing, it will knock out one of these train cars. So it pushes the train car out, and look at that. There are the two atoms that were holding this together. One on top, one on bottom, and the two atoms holding this together. So those were like the two pins that were going between the junction piece holding this together. And so again, here's the crossed conformation. Now, you see this is in a trans state. Because of that, the copper atom can't reductively eliminate, can't come out of there. We tried manually pushing this into a cis state, hoping that the copper atom would get thrown out, but it still never came out that way. It just didn't have enough freedom to get the orbitals lined up right to do that reductive elimination, where if it's in solution, it has all this freedom. Here it's stuck down to a surface. And here's the height of the two add atoms. These are the two copper atoms that were holding that in place. So the question comes, could you race these cars? So we wrote an article on how to build and race a fast nanocar. I mean, you ever think you could write a scientific article like that? this was like, I think it was like in Nature Nanotechnology or something. But what we did is we built these cars, and you say, okay, here's the cars we built. So it's not much of a car, it's only got 2 wheels. But we knew we had to race these. There was a race in France. The first international nanocar race was held in France. And we had studied the movement of molecules on surfaces, and we knew the more wheels you have, the more it sticks to the surface. So you want to minimize the number of wheels. So we went to this 2-wheel structure, and we put an amine here and a nitro group there, so it'd have a strong net dipole. And that strong net dipole would allow it to be influenced by the tip more easily because the tip is setting up an electric field gradient. And that's the idea. And you can see here's one of these nanocars, these 2-wheel things, and it's kind of bent. But you see how it's kind of bent on, it's sort of like a bean, kind of curved around. Okay, so here's the wheels, the axles, and you have this strong net dipole. And because when the electron charge is pushing this way, this methyl group and that methyl group are going to sterically push these axles further away, and that's what gives you that little bit of bend. All right, so everything is making sense here. And so here is the racetrack. And so what you do is you put some molecules down on a surface, and then you just look around to find your molecules. Okay, so here's one of the molecules, one of this sort of bent things on a surface. And so you say to the judges of the race, okay, we're going to race this one. All right. So when we were racing that one, so they require you to have 2 pylons at a certain distance away from the car, and then a end gate. So you come over here and you touch the surface with your STM tip and you pull up an atom. And so that's an atom that's been pulled up off we were actually using a silver surface, and most people were using gold, but we had to use silver. And the reason was that gold stays much cleaner. Gold doesn't get adsorbates very easily. And so you can go much faster on gold, but our car was too fast for the surface. It was too fast for the track. It would just move way too fast. It was uncontrollable. So what we wanted to do is we wanted to say, well, let us change the amount of voltage pulses we can. But no, they had certain parameters. So they penalized us. They said you have to use silver, which is a much slower surface. But because of that, you have to go, instead of 100 nanometers, you've got to go 150 nanometers. So they penalized us 50 nanometers because we got the slower surface. Because what happens with silver is you get adsorbates from the air. You can get like CO2 and CO adsorbing to the surface, and those adsorbates slow you down. But in any case, this was the one pylon, here was the other pylon, and here was the end gate. And so we drove it this way, around the other pylon, and then through the end gate. So you see it was there. So it started out here, and it ended up there. And that won the nanocar race. And so, yeah, that was it. And it took us, I don't know, it was like 90 minutes. Yeah, it's an hour and a half to do that, to go the 150 nanometers. Now, the next one behind us was the Swiss group. They came in 5 hours behind us. And none of the other groups, the international groups, was able to finish the race in the 30 hours of the race. And actually, that year, they were really upset because they had film crews and everything that were going to stay there for 30 hours. An hour and a half, we were done. I mean, we just already did it. And that's because we had a big plus. We had been studying these sort of molecules on surfaces for a long time. It wasn't just a new thing for us. And then after the race, we wrote an article. Okay, here's how you do it. Here's the things you want to build in. And so the things you want to build in is you want to build as few wheels as possible, and a strong net dipole, and fully rotating axles. All of these features we said you want to build in, knowing that the next year it would be much harder for us. And then they put other requirements. Well, it wasn't the next year. It was like multiple years later, and then COVID got in the way. But anyway, they put certain requirements, so we couldn't use this car again. We had to have a much larger car. It had to have a certain number of atoms or something like that. All right, so what about motorized cars? And so the idea is that there are these motors that were developed by Feringa, and in fact, he won a Nobel Prize for these, and I think it was in 2016, something like that. But the idea is that you can shine a light on these motors and they will only rotate in one direction, so the unidirectional rotators. And that direction is controlled by the chirality at that stereogenic center right there. And so what happens is when you shine light on this, that double bond right there, you get an excitation of the alkene and it will go orthogonal. Boom, it goes orthogonal. Now, there's a methyl group hanging out off there. That makes these two directions in spinning the rest of the way around diastereotopic, because you might remember that propellers are chiral, so you have a chiral element at the propeller, and then that methyl group, this is a stereogenic center right here. So there is another chiral element. So when you have the two chiral elements, now these two directions are going to be diastereotopic, different in energy. And so it spins around in one direction, spins around, and then you can photolize and continue this and keeps going in this one direction. I don't know if this thing's going to load. No, it's not. Anyway, so it spins around in this, and so we thought of building this at mid-chassis. So the idea would be to build this at mid-chassis, have it spin and push the car forward and have it go in that way. We could have built this into the chassis. So you see this is at mid-axle, and this thing would spin. We could have built this into the wheel, but it was operationally much harder to do that. So we just sort of thought this would be like a paddle wheel pushing it across the surface this way. And so this was the first motorized nanocar to be made. So we made the first nanocar, then we made the first motorized nanocar. This first nanocar was made in 2005. We published it. 2006 came out with the motorized nanocar. But the thing is, it didn't move very fast because that motor only rotates at 1.8 revolutions per hour. They're not a very fast rotator. But Feringa had published, if you just take out that sulfur atom and close this down to a 5-member ring, now it's going to spin at 3 million rotations per second. That's pretty good, right? 3 million rotations per second. So we built the Feringa car without that sulfur. You can't just rip that sulfur out. It'd be great if you could. You have to go back all the way to the beginning. And here's the synthetic route to do this, to get that 5-member ring on one side, and then hook these things on. Here you have your axles. And we use NMR to tell us, to give us information about these molecules. So those of you who've taken organic chemistry, you'll understand that you have these small couplings here, but you have something called the NOE effect, a nuclear Offenhauser effect, NOE. And through that, you can tell by the closeness in space, by the extent of the NOE effect, by the strength of this NOE effect, you can tell the arrangement here. So we can characterize it by NMR, and here there are two different routes by which we could go, but we got the motorized nanocars, the fast motorized nanocars. And again, these would have the cross conformation or the parallel conformation, because you see that if I spin this around this bond here, this wheel is going to end up here, and this wheel is going to end up down here. And so these two now would be anti-parallel. The parallel is going to be the lower energy conformation, so you see more of the parallel. So there's the 4 wheels, there's the motor, and then here's the 2 4 wheels, and then you have this motor sitting in the middle, and here's the cross conformation. Now, imaging those took years. It took years to really get good enough that we could control motor rotation on a surface. That took a long time. And there were a lot of reasons for that, because you'd go to excite the motor, it would electron transfer to the metal surface. And rather than causing rotation of the motor. Then we thought, could we have a hydrogen-fueled nanocar? So the idea is if we had a metal catalyst on the end, take hydrogen and ethylene, and that would form ethane, and as it's throwing out ethane, it would act as a fuel source to push it along. That was sort of the thought. Think about that. You have all these synthetic tools now, and then you're just trying to think out new ways to propel a car. And so we made this such that it had this rhodium catalyst on the end that could do this. But now we'd have to go into an STM apparatus. And our early work in STM was done with Kevin Kelly, who's in the electrical engineering department here. And then later on, we started working with a group in Austria, a group of Leonhard Grill. But this is very hard to do because you have to feed in ethylene and hydrogen. So the imaging just never got done. And then we also thought, well, if we could polymerize off the tail, what if you could feed in a monomer and just start growing a polymer, and that would push the car along. Once the polymer got large enough, it would stick to the surface and the car would get pushed along. So you sort of have like a string hanging off the back, but it would push it forward. And so we built these. We built these with polymerization catalysts off the end of the car. And so here's how we built some of these things to design them up. And Yasmin Godoy built these. And so we could build these cars this way with this polymerization group, and we could show that in solution, indeed, these are polymerizing. You would convert this monomer into the polymer, the cyclooctadiene to polycyclooctadiene with the nanocars. But this was all in solution. Again, doing the surface chemistry is a whole nother ballgame. And then we wanted to see, could we begin to change this? Because we're using scanning tunneling microscopy. That's a difficult experiment. It's usually done in ultra-high vacuum and all sorts of constraints upon you. But if we could make the nanocars fluorescent, if they're fluorescent, they're going to light up, then we could think about driving these just on a glass surface, just a glass cover slip. These could be very flat, long, flat terraces. And if we could see a fluorescent tag, the problem with fluorescence is you're never going to see the definition of wheels and chassis and stuff like that. It doesn't have the definition for you. And the reason it doesn't have it is because that fluorescent light will be, while the car is like 2 nanometers in diameter, that little fluorescent glow could be 100 nanometers in diameter. So all you just see is a big light. But still, you could watch it in that way. So we put a fluorophore, a tritzy, on the end of this because that fluoresces. And so here's the nanocar. And then once you put that tritzy on there, it starts absorbing at 532. And once it's absorbed at 5, and now this is a highly fluorescent molecule. And so what happens is, if you just put tritzy on a surface will be the red material that doesn't move very much. But when you have the nanocar, it moves a lot. So there's the blue, there's the red. And so what happens is, as a control, you just put the fluorescent molecule on a surface and you see how much does it just move around on a surface at room temperature just naturally. And this was with Stefan Link's group, who used to be at Rice, and he's recently moved. But then you put it on a nanocar and it's moving all over the place, such that we could record that it was going 3 nanomiles per hour. Or about 4 car lengths per second. So if a car is moving at 3 miles an hour, it might go about 4 car lengths per second, something like that. All right, and then we made, instead of having this big ball and chain, this big fluorescent molecule hanging off, I thought, well, why not make the car itself fluorescent? So it itself, you could shine a light and it would start emitting light from it. And so instead of going from the tritzy tagged, we'd put this molecule on there so that it would fluoresce inherently. So the fluorescent group, in this case a BODIPI, is really part of the car itself. it's part of the axle of the car. And then we changed the wheel structure, and the wheel structure would allow it, when we have these different wheels on there, it would allow it to go faster. Then we thought, well, could we make submersible nanomachines and drive them along? And I thought it'd be really good if we could do something like this. You know, I was hoping that these nanomachines at this level, if we could make them so that they'd be yellow, we could call it yellow nano submarines. And you guys don't know what yellow submarine is, but okay, you do. Okay, all right, okay. So I thought it'd be a great title, yellow nano submarine, but they weren't yellow. And then I tried to get the Navy to get excited about this. We could make, 10 to the 18th submarines. So people had looked at molecules moving in solution, particularly not molecules, but nanoparticles. And they had they'd taken clusters where you had gold on one side, silicon on the other, and they'd do polymerization off the edges, and they'd try to move things along. Ayusman Sen at Penn State had done a lot of work on this sort of thing, and others have. And so we weren't the first to try to think of things moving in solution, but we were the first of trying to track single molecules moving in solution, rather than nanoparticles, which are much bigger than a single molecule. So there's a lot of challenges in that. These nano submarines are going to be less than 10 nanometers in size. How do you track them? And what's the mode of propulsion? So again, working with Stefan Link's group, what you could do is you could take glass slides, and you could put spacers on the glass slides, which are just polystyrene nanoparticles. So you just have a tiny little bit of solution between two glass slides, and the only distance between those two are nanoparticles that you can't even see these particles, and so you just have a very small volume there, and so you can have a very small volume, or you could have something just a few microns in size, so you can barely see these things, and then you have your liquid with your submarines in here. In this case, it'd be a water solution. And you're tracking now the molecules as they go through a certain volume of this. Just when they go under this, in the midst of this this lens, as it's going across, and it's got this fluorescence. So what happens is the molecule goes across, and it's going to spend some time in that volume. So when it spends time in that volume, you're recording the amount of time that it spends in that volume. And it might spend less time in the volume, or even less. So by the amount of time that you see it in this field of view, from that you can back out a diffusion constant, how fast this thing is going around. So here was the nano submarine we were going to make. It had the Feringa motor sitting there, and we just modified the Feringa motor so we could build it into these structures. Then we did what's called a click coupling on each side, and then we had these big fluorophore pontoons, and we had two of them. Because if one of them dies out, in other words, if one of them oxidizes or something, you still have the other one. And so it had like two lights on it. And the idea is, this is the rotor, this is the stator, and then this is what's tracking it for us. And so we built several of them. This was the Unimolecular Submersible Nanomachine, USN, Unimolecular Submersible Nanomachine. This is the one that has a spinner that when you shine a light on it, it spins at 3 million rotations per second, so fast. We built one that has no rotor on it as a control. So you need something that doesn't have a spinner on it, so there's nothing there. We built one with a slow motor that's 1.8 revolutions per hour. And then we built one without the methyl group. You see, this one has a methyl group. This one has no methyl group. Without that methyl group, there's no secondary chiral element. And so when this thing excites into the orthogonal state, it can go either way. So this would sort of be like flapping. There's no directionality I mean, sometimes it would go around, sometimes it would go the other way, just mainly flapping. And so you'd think that that wouldn't be as effective in propelling this through solution. And it turns out that we looked at the diffusion, the time that it spent in that little microliter volume area. And you could track this out, and it turns out that here's the USN1, the one with the fast, it was moving 26% faster than a normal molecule should diffuse in solution. At the time, and it might still be the case, this was the fastest moving molecule ever in solution. To get something to move 26% faster was a big deal. The flapping molecule was moving 10% faster. And then the other two, the one that didn't spin and the one that had the slow motor, it didn't go any faster at all. So it made sense. You know, you make a control and it doesn't do it, and you do this and it does it. So then we had to think, you know, what is the way that this works? How does this work? And there were a lot of theorists that were coming up with different ideas on how this spinning thing in solution, you know, you'd think it's spinning here and it's pushing this along, but that's probably not it. What they came up with, it's like think of walking across a basketball court, and everybody in the basketball arena is throwing basketballs at you. All right? So it would be hard to walk, wouldn't it? I mean, you're getting pelted by so many of them. That's what this is. This molecule is wanting to move, and it's getting hit by water molecules in solution. So it's different than driving a car on the surface at ultra-high vacuum where you don't have many things hitting it. And so how does this thing move when you have so many little smaller molecules, these water molecules, hitting it? And the idea was that this thing spins, and as it spins, it's knocking these water molecules out of the way. And then the water molecules behind it are pushing it to fill that void. So it keeps pushing it to fill the void. So this is actually moving in this direction. That was the thought. You can't tell, but the velocity, it's about 15 meters per second. You know, so that's very fast. If you think about it, I mean, these things are moving very fast, but then they deflect. You know, so it's not like 15 meters. No, it's very fast, but it just keeps getting deflected. It's like you know, basketball is being thrown at you. It's just going to keep knocking you in different directions. All right, so these could be driven fast, and they could go in this fast directionality. All right, so we had built in a lot of different elements into nanocars. We had built in cargo transporters. We had looked at different fuel sources, light to shine on it. We had, I remember we built in different polymers that we wanted growing off the back end. We had little wheels, medium-sized wheels, big wheels. We had suspension that we talked about last time, this ability to spin. We had the axles and the wheel bearings and actuation sensors. When we had these little trucks that could bind certain things. And then we had the motors, the Faringa motors in there. So that was that sequence.
So just to clarify, you won that first Nanocar race?
Yeah, we won the first Nanocar race. We didn't win the second, but we made a good car. I mean, so we just made the car. So the second race was like 4 years after the first, something like maybe even 5 years, because COVID slowed it down for several years in a row.
Was it a race here in the U.S.?
No, it was in France, and I wasn't going to go to the second one. You got to go to France, and we had let me unhide this thing. So the Austrian group was driving the car for us. They're experts imagers, and they met us in France. Going Austria to France is a lot easier going from Texas to France. And so I was there in France that first year, and you know, the students there were driving it, and so they had these STMs. They had 4 STMs in France, but that wasn't enough for all the groups. So the group could drive the STM at their home location via the internet. So your control had to be there. Your control system had to be in France. But you're controlling, your computer had to be in France. You're all sitting in the same room. But your STM was in Austria. But you're controlling the tip of the STM, and you can't touch the car with your tip. You can only put the tip in front of the car and pull it. And the clever thing that we had in the first race, but then we taught everybody how to do it. So we knew the competition would be much harder the next time. So most people would give a voltage pulse, the car would move toward the tip, and then they'd come and image. So now you got to scan back and forth, make sure the car went in the direction that you want. What the Austrians had figured out, don't do that, because all the time is in imaging. So they would look at where the car is, and then they'd give a voltage pulse, so the car moves toward the tip, and then they just move the tip out, give another voltage pulse, without looking. They just assume that the car is following. And then they'd come back after, 10 or 20 pulses, and they'd come, all right, where's our Nanocar? And they'd look around. Sometimes the Nanocar never moved on the first pulse, so it's still way back over here. But that was still saving a lot more time than constantly rastering back and forth to get you the image, because it takes about a minute to raster back and forth and get the image. So so we described that driving technique. The other thing they tried to do, now, none of our cars were allowed to have motors in them. None of our motorized nanocars, because nobody had ever made other ones like that. So we couldn't use our motorized cars, which could be really fast. We could activate them. Plus, we wanted to use an AI program to do the driving. And they wouldn't allow us to do that. Everything had to be hand-driven. So, there were a lot of constraints the second year, so the students were all bummed out. All the fastest stuff that they had couldn't be used. But anyway, I wasn't there the second Nanocar race, which I think was just last year, in 2023. Okay, so we had seen these before, but then I met this guy. So what happened was I had tried for a long time to take these nanomachines and have them drill into cells, drill right through the lipid bilayer of a cell to kill a cell. That's what I wanted to do. I wanted to kill cells with these nanomachines. We don't need the wheels or anything. We just take the motors and have them drill into cells and puncture through and kill them. This would be a great way to kill cancer, right? You have cancer cells and target it to a cancer cell. And I was asking around a lot of people, who were good at this. You had to know how to work with cells. You had to know how to work with imaging systems. And these were fluorescent enough that we could watch them, so using a fluorescent probe. Then I met Robert Powell, not at the rodeo. It's when he came to the U.S. that I took him to the rodeo here. But I was a lecturer at Durham University, invited to give a one-week lecture, and so I was giving a different seminar each day. And one day I was talking about the nanocars. And I had been asking one of the professors there, who I thought could really pull this off, hey, I'd like to drill into cells, we get a collaboration going, we'll make the molecules. And he said, at this stage in my career, I'm not sure I want to do it. It's a big job. He says, but I have a postdoc, Robert Powell, who's the best experimentalist I've ever had with me. And Robert had just gotten a job in the university as a lecturer. A lecturer in the UK is sort of like an assistant professor in the United States. They start out at lecture. And so I talked to Robert for 10 minutes or 15 minutes at the end of a seminar, saying I'd like to try to get these machines to drill. He said, okay, send me a sample, we'll work on it. I sent him the sample. When I got back to the US, I sent him some samples. And back in those days, this was 2015, we didn't have to have all these forms filled out for mailing samples to her. Now we have, lawyers mess up everything. You got to have non-disclosure agreements, material transfers agreements, and all of this stuff. So anyway, I just sent them this, and within 2.5 months, he had gotten it working. So the idea is that you put one of these molecules on a lipid bilayer, and then you turn these on, and they would spin, and they would drill through and pop holes in the lipid bilayer. And if you pop enough holes in a lipid bilayer, that cell is going to die because you lose your whole ionic potentials differences, so it's going to die. And you can actually see this. You look at it, here's a cell, and you see a time course here. You see these little bubbles on there? Can you see those? Can you see little bubbles on there? Yeah, that's called blebbing, and that means that that cell has a hole in it, and the guts are just squirting out. That's what that means. So these cells end up undergoing necrosis. They don't undergo apoptosis. Apoptosis is a controlled cell death. It's controlled. It chops up the proteins, it chops up the chromatin, and then it slowly dies. Necrosis means that boom, they just explode, and they can't chop up their DNA, they can't chop up their proteins, they just die. And these would necrose that way. And so you can see this as a time course. So we just took these nanomachines. Look at these nanomachines. We took a control that doesn't rotate, and we had different end groups on here, and we used it in the presence of propydium iodide. So propydium iodide is a dye that turns red when it intercalates into DNA or RNA. Now, the only way it can intercalate into DNA or RNA is to get inside the cell, but it can't normally get inside the cell. So you put this in the medium with the cells. So this is just in a dish. It's not in a live organism. It's just cells in a dish. And you put propydium iodide in that dish, and it's not lighting up. But once it gets into the cell, boom, it'll intercalate in DNA or RNA and light up. So it's a probe to tell you when the cell is opened up, because there's propydium iodide, but it's by itself only gets in very slowly. And so in the blank, there's no propydium iodide going into this thing, and you shine a light on it for 15 seconds, 300 seconds, 450 seconds, 600 seconds. So then what happens, this is the time that it took to necrose. So the time that it took to necrose. And so what happens is, as you take this molecule 3, the time that it took to necrose, they started to necrose almost instantly, and the later ones, by the time they were done, it's here, starts here, ends here. And so it's happening much more quickly. And you can see the propydium iodide flooding this was just time to necrose. Here's the propydium iodide added, and you can see the propydium iodide just moves right on in, and it goes in and it even gets into the nucleus of these cells. So these are PC3 human prostate cancer cells. And so you can see that they get in, and then they allow propydium iodide to get in. And then we put these peptide addends on them, because you can look up in a book, you can say, okay, we're trying to kill PC3 cells. So it's okay, if you want a recognition for PC3 cells, PC3 will overexpress this glucose-regulated protein on its surface. So we're targeting this, and it's a 78,000 kilodalton glucose-regulated protein. So if it says, okay, this sequence of amino acids, this short peptide binds to this. And so we just order this peptide from a company, and then we coupled it through what's called a click coupling onto the ends of this nano machine, this rotator. And some of them we coupled on 2 ends, some we just coupled it on 1 end. And so now it should recognize it. So we're exposing it to 3 different types of cells: the PC3, the human prostate cancer cells, NIH3T3 cells, which is a breast cancer line, and Chinese hamster ovary cells. And but it should target just the PC3 cells because of this sequence here. And we could do that. So I don't have the slides here. I'll put them in for next time. But it would target just those particular cell types, and then you'd see them start going after those areas, and then we started killing the cancer cells, and that turned out to be a big deal, and we ended up starting a company around that to kill cancer cells and to kill superbacteria, which we'll talk about next time. But and then also treating cells. So you just pop a few small holes and you have drugs in there. So this opened up a whole new area. So we had set out to try to do construction with nanocars. That became very difficult because of the manipulation. But what turned out from this was to take the motors themselves and use it to go after killing cells in solution, rather than you don't need the wheels here anymore. Are there any questions? Well, this is nanotechnology at its finest. Okay, see you next time.
If you're enjoying this series, give us a thumbs up and click the subscribe button, and that way you'll hear when we're coming out with new videos. There are no salaried employees in this organization. All the accounting, all the legal work, that's all done by friends of mine. The only thing that I have to pay for is the production work, and if you could help us out with that, I'd appreciate it. There's a link below where you can just click on that and help us in several different ways. Thank you.